Hello, this is a new update in the series of videos where I design and build an Arduino integrated robotic arm project. In this video, I will show final prints made, any adjustments to the design, and electrical components and demonstrations of the robot arm thus far. This video is long overdue due to several issues I was encountering with completing the project, and other things along the way that I'll bring attention to later on. Based on much needed adjustments for the claw assembly from the previous video, new prints were made, including one for the holding plate that accommodates room for the MG995R servo motor instead of the SG90 servo motor. As explained in the previous video, the SG90 servo motor could not provide the sufficient torque needed to enable rotational movement to the claw components for opening and closing actions, often malfunctioning once surpasses max torque threshold. To remedy this issue, the MG995R servo motors were put in place for the grapper servo as well as the pitch servo. A new print for the pitch components was made as well to reflect these changes. Another additional change made was replacing the wrist servo with the MG995R servo motor as well, as it became clear that in redesigning the claw arm components, the additional weight supported by the wrist would be too much for the SG90 servo to handle. A new print for the first and second joint of the robot arm was made subsequently for including these servo motors instead. The second joint was also substantially redesigned to reduce its length and mass to support the remaining claw assembly. This was done to reduce the max torque of the linked system on the second joint servo motor below its stall torque of 11 kilograms per centimeter, the point at which the servo motor would typically fail. Another minor change made was to the support hooks. Before, both ends holding each other were open on one side of the hook, allowing for a band to hold them together. However, after doing some testing, the hooks would begin to bend towards the side that was open due to the stress exerted on them by the band. To mitigate this issue, one hook would be closed on both ends, while the other one would remain open on one end. The hooks open on one end were incorporated into the design and print of the first joint. On the electronic side, a couple of changes were made. For the transmitter and the receiver, a 10 microfarad capacitor was soldered across the power supply line of the NRF24 modules. This was done in order to reduce noise and delay in the channel communication and increase the range of the modules. The capacitors help with decoupling high frequencies of the radio module, stabilizing any oscillations as a result. When testing, all the components worked almost fine with the new changes. The grappler and pitch servo assemblies moved without any substantial delay from the input of the rotor encoder to the receiver module. Movement would become more smooth and controlled compared to before, which was more erratic. The servo motors would still sometimes lock into place or move irregardless of input. This was primarily caused by poor connections between the different components on the breadboard. At this point, I decided to instead handle the electrical components on a PCB or perf board. Perf boards typically had better current carrying capacities compared to regular breadboards, and it makes disturbing connections less likely. To duplicate the transmitter, a 7 by 9 cm perf board is used for soldering each of the components. Pen headers are attached first onto it for placing the Arduino Nano. A rotary encoder is placed left of the board, while a slider switch is placed on the other side to turn on or off the power of the transmitter. A 3.3 volt power regulator is placed beneath the board, which will control the voltage and current supply to the components. Two decoupling capacitors are placed parallel to each other, connecting to the 3.3 voltage regulator to stabilize the current. The NRF24 module is placed on the other end, and jumper wires are soldered between corresponding pins of the module in the Arduino Nano and the 3.3 volt voltage regulator. A push button is connected between the ground and the signal pin on the Arduino. The program interprets any changes on the button and sends it to the receiver end. This mechanism indicates which servo motor to control within the robot arm assembly. This helps with controlling different joints of movement independent of each other with as few input components as possible for the time being. A 9-volt battery connector is also placed across the slider switch and the voltage input pin of the Arduino to provide an external power source to the transmitter. For the receiver, the servos of the robot arm are hooked up onto an external power supply on the perf board for better current carrying performance. One row would connect the ground pins, and the other row would connect the 5-volt power. The external power source will be run by a source of 4 AA batteries. The receiver portion of the project is composed of the robot arm assembly, an NRF24 receiver module, and the Arduino Uno hooked onto a breadboard. The Arduino Uno controls the movement of the servo motors within this robot arm assembly based on data from the receiver module. Despite my subpar soldering skills and a couple issues with arranging the circuit design, the overall circuit was able to work well and transmit data to the receiver of the robot arm. With this, I'll bring this update video to a close. At this point, the project is nearly done, and all the prints and assembly worked out with. A subsequent update video will be posted to bring this series to an end. If you liked this video or have any suggestions, leave them in the comments below. And once again, thanks for watching.